Jordan and Mathias and I are delighted to present ship-to-ship transfer detection using machine learning. Maritime transport completely underpins the global economy. 90% of global goods, 60% of oil shipped, over 50,000 vessels are active at any one time. Transfers often, transfers, transfers between the ships often occur. And it's actually a very important function to reduce port congestion globally. The aim of this project is to detect these transfers. Most of these transfers are legal. However, as you might imagine, there's a significant minority which aren't. Nation states seeking to evade sanctions can use sea-to-sea transfers in the ocean to offload goods and sell them. The goals of this project, to source and curate an STS transfer dataset, to identify and train a convolutional neural network, to build a machine learning pipeline to detect these transfers, and to connect these predictions with another data source, AIS, which will allow us to identify the vessels. And obviously, to conclude with reporting these findings on the dashboard. And I'll pass over to Jordan.
So before we take a quick tour at our applications, I will talk to you a bit about the data that we used for detecting these ships and those ship-to-ship transfers. So we use satellite images. So we collected data from Sentinel-1, which is a satellite of the European Space Agency. And this satellite in particular collects what is called SAR data, synthetic aperture radar. And the benefits of using this data is that it uses microwaves and which makes them like all weather and day and night data, which like tackles the limitations of like normal optical imagery where you cannot see through clouds. So this like penetrates through clouds and can see also like day and night. And this data in particular is a resolution of 10 meters per pixel, which is rather low, but good enough because like our ships are like sometimes hundreds of meters long. So you could get like much higher quality data from commercial providers. But the good thing with this data is that it's really available and accessible. So good point. The next type of data, okay, I've been to this weather agnostic day and night. The next type of data that we use to actually identify the detection of the ships that we detect with, sorry, I forgot to mention. So this is like basically like an image of the ship-to-ship transfers, and this is what it looks like on SAR images. And this is what our model has been trained to detect. And now the automatic identification system. So this is what Jose mentioned, is this geolocation data that is provided and shipped and transmitted by ships at every second, and that is collected either through received by satellites or terrestrial receivers. And this data, unfortunately, doesn't come for free and is actually very expensive. We contacted all the wholesale providers that actually have this good quality and high frequency data. And to give you like an idea, for 1 month's worth of data for like the Eastern Mediterranean, it was about 1,400 euros. That was a limitation for our project, so we didn't go for this and found actually another provider with a much lower frequency where we could access like historical data, but at a much lower frequency, which basically impacts the results. But without further ado, let's have a look at the app, our application looks like. So at the heart of our application is an interactive map that brings to life the detected vessels and, more importantly, like the ship-to-ship transfers within this area. The area that you see on the screen is called like the Laconian Gulf, which is located in the southern Penopolis, which is in Greece, in South Greece, it's in the Mediterranean. And why did we choose this area in particular? It's because it's very well known as being a hotspot for ship-to-ship transfers, and also like has like a very high maritime activity and traffic. So we would expect to actually see quite a lot of things happening there. And in fact, we did. And also, just the basic features of our app, as you can see, like on the left side, the user can input like a date range. At the moment, we have like 2 years worth of data, starting from February 2022 up to date. And you can filter. And when you click on filter, you get like, you can receive a short summary of our findings. So the number of ships detected, the number of ship-to-ship transfer detected, and other useful information. And also this app includes at the top like a navigation feature. It allows to move seamlessly between frames, different frames within the date range that you chose. And yeah, the data that you see but at the heart, actually, the best or the most innovative feature of our app is actually the possibility, the ability to visualize the satellite images that were detected by our model upon user interaction. So when you click on a data point, you can actually see what the model detected. And the red points are for ship-to-ship transfers. And you see, like, when you click on this point, you see what the 2 different ships that were detected by a model. And if you click on the green dot, you will actually see what the model detected. And it's a ship. You see, it's a single line here. But on top of that, what's also what our model does, or what our app does, is that it connects with and identify the ship that is the closest located to the detection. And this data comes from the AIS data. And this is the day where I forgot to mention that contacting all these wholesale providers, one of them gave us 1 day worth of data, or maybe I did it already. And so we can see like the time delta comparing to the timestamps for our SAR image is very low. And hence, therefore, like these dots are almost overlapping. If you switch to a different frame, this is like the other source of, normally you can navigate to a different frame. And what you would see is because of the lowest frequency of the data, you would say, and also like you see like how like let's say like those dots would be like much further away, and it would be like it would be like very much more difficult to identify with with high confidence which ships are connected to those dots or to the detections of our satellite images. And lastly, that's wraps up our application. So we think we're still at the stage of a proof of concept where we see like it has great potential with high quality data and high frequency AIS data. It could definitely be used, find use cases for maritime authorities, for instance. And one thing that is probably worth mentioning is that AIS data, or ships must transmit those AIS data, but sometimes they actually, that's the lower quality data. And as we can see, like, points are getting further apart as the time delta increases. But one thing like where like our model could be like very useful is like scanning areas where we know like illegal transfer or mainly happening, and to detect if it's actually it's an illegal ship-to-ship transfer. We would like detect with the satellite image, and you wouldn't have the AIS data, because usually what this ship does is that they turn off the transponder to go dark, what is called like those dark vessels. So that would be like one interesting use cases of our model.
For the first part, the image preprocessing. So this is a picture of the raw satellite image that we get from Google Earth Engine. It's in decibel scale. And in order to preprocess this, we just clip the image by at between -30 and 0 dB. And then we stretch the image or min-max scaled it between 0 and 255. There are different ways of doing this. There's quite a lot of literature about this, but this yielded the best results, so we just stick with that. Then we put a land mask on the land, because otherwise we would have a lot of false positives.
on the land. Then we split the image into smaller tiles to input it in our model. Because this image is quite large, it's like 6,000 by 5,000 pixels. Already just a smaller part of a big satellite image that can be up to 20,000 by 20,000 pixels. Yeah, this is just an example of a tile, how it would look like. We had to create our own data set because there's nothing out there to really differentiate between ships and ship-to-ship transfers. So we labeled about 600 instances of ships and 100 ship-to-ship transfer. We chose YOLO for the model because it's high speed, it's super easy to use, and resource efficient. Yeah, for the model evaluation, so our model had an accuracy on ship-to-ship transfers of about 86%, and it's 93 on the ships, so quite good. And yeah, for the conclusion and next steps. So for the sake of time, we only had 3 weeks time, so we just stick with YOLO for the beginning, but it would also be interesting to do a benchmark with other models like faster RCNN, for example. At the moment on our dashboard, we just pre-predicted a few, all of the images that we have, like it's almost 200 images, right? But our pipeline, you can also just pick a date, get an image from Google Earth Engine and predict it, and then output the data on the map. But can be quite slow. So sometimes it takes like up to 15 minutes to get an image from Google Earth Engine, because they can be up to 4.4 gigabytes per image. Yeah, and if you really get the money in your hand and get good quality AIS data, we see there could be a commercial, potentially commercial use case, especially for maritime security for authorities to enforce legislation, for example. And Hasso-Platter Institute was interested in to develop this further. And maybe something I also mentioned at the beginning of the project, we had a little bit of a different approach. So what we wanted to do at the beginning was we wanted to do more kind of anomaly detection on AIS data and then track them with satellite images. But since the data was so expensive, we couldn't really do it and had to yeah, do it this way. Yeah, we want to thank you, DSR, for the 3 months of intensive teaching